Okay, let me get the share link. Share, share, copy, put it on Slack. Did you guys receive the YouTube link? I hope so.
Yes.
With that in place, I will now start the recording. And all right, folks, today we have to do the lab for automated machine learning. Now, automated machine learning, we covered a bit of theory. I'd like to finish that theory to some extent. I may not cover all the details of the TPE, the tree structured parser and estimator. We'll keep that maybe for Saturday or sometime later, because otherwise we'll get derailed. Today, our main goal is to do the labs. Now, automated machine learning or auto AI, auto ML, many such words that people are using. It's a very active area of research and development. You see so many papers coming out on it. You also see a lot of libraries coming out on it. I mean, there's an entire website, I believe it's automl.org, that catalogs all the different um, AutoML libraries that people have created. I have posted that. You'll find links to that on the course portal. And when you go there, you'll be surprised how many libraries are coming up with it. Even for a library, mature library like scikit-learn, which we have all been using, it comes as a surprise for you, perhaps, to learn that people have been creating automated machine learning versions of scikit-learn. They're saying, let's make something that is so easy to integrate with scikit that people don't even realize it. The learning curve is close to zero. And so I'll pick one of these libraries. There are many. There's auto scikit-learn, there's scikit sk-opt, there is uh, scikit optimize and sklearn optimize, and so on and so forth. There are many of them. And then there are independent libraries, like, for example, hyperopt, and then there is the teapot, and many mature and very good libraries are emerging in this space. A lot of excellent work is being done. Now, while all that excellent work is being done, when you play around with these libraries, you realize that a lot of them, not all of them, but a lot of them have very rough edges. Those libraries are nowhere as mature as PyTorch or scikit-learn. So the mileage varies. You try, and what you will happen is today can be one of the more frustrating labs for you, in the sense that a lot of these very promising libraries, they will tell you, pull the code from GitHub, right? The library literally from the GitHub, clone it from there, and then do this and that installation step. And then if all the stars in the sky are aligned, it might work on your laptop. Right? So in other words, they have a lot of rough edges, and it takes some amount of effort to make them work. Right? So with that being true, what I did is instead of picking the most sort of dominant libraries, and I'll talk about them and go through some examples. I will talk about a few dominant libraries. I picked the ones which are the least frustrating, because our goal is to learn to walk before we run. Right? So picked the lab based on simpler libraries, gets the work done, and are promising, very promising. They too are in the whole race. Um, and so we'll proceed from that, and I'll take some examples from that. What you will learn is that it's a very rich area and lots of people are coming. Now, while for many things, for all other parts of AI, I have sort of, I have a distinct and huge advantage in the sense that I've been doing it, practicing it for a long time and carrying it forward. When it comes to auto ML, the things are happening so fast that quite likely the tables are turned. Once I teach you what I have to teach, the theory, of course, I will teach you properly. But when it comes to the practice, the actual libraries that people are creating, and so on and so forth, this is an opportunity for me to learn from you guys. And let us form, and I want to do this lab in a slightly different way. There will be some things I'll do in common. And then what I would like to do is make this lab into mini projects. You guys have already the project teams. What we should do is divvy up the many, many libraries that are doing AutoML. And each team can pick up a couple of those, post it that we are going to create examples using these, right? And let us all evaluate all of these libraries, right? It is not a simple task to sit and evaluate all the libraries, and nor does one person have the time to do that and go through the frustrating setup. But if we
Libraries
do it
and
as a
frameworks?
project, if we all come together and like one group takes two or three libraries here and does pretty much the same example, MNest or this or that. Another group takes something else and then they do a few of those. We can quickly create notebooks that cover the whole gamut of these emerging libraries. Are we together, guys? And so that is the approach I would like to take. That way, we will all enrich. It will be collective effort. We'll all enrich. We'll create a collection of those notebooks on our course portal. And with those notebooks, we can all benefit from each other without going to the frustration of installing all like a 2 dozen libraries or 3 dozen libraries that are emerging in this space. So does that sound like a good plan, guys?
Yes.
Okay.
Um, Also, frameworks that we've learned about too.
Yes, yes, all these libraries and frameworks. Yes, that's
Okay,
right.
great.
And also, guys, like the paper, like for example, I believe was it you, Kate, who brought about the Auto Zero, Auto ML0?
No, I know about the Newton
Uh,
framework,
the,
company that has a
Newton,
framework
which
for
again is
AutoML.
very good. So, guys, at this point, what is happening is things are just in a process of exploding. They just sudden explosion of interest and libraries and projects and companies getting into it. So let us bring or help each other in coming up to speed. Who pointed out Auto ML0? I forgot. But Auto ML0, I think Pradeep, it was you.
Yeah, Asif, I am Praveen.
Oh, Praveen, yes, you did. So let's do one thing. See, in fact, I was thinking that I'll cover Auto ML0 for this coming Saturday, coming Sunday paper reading. Let's read that blog through. Right? We'll review that blog. It's a very interesting paper. It's very early work. The success is still far off from a very practical perspective, but very promising work in the Auto ML space. So let us review that. So as you guys explore this topic, and I would tell you that take this topic very, very seriously. It can be your differentiator from the crowd. At this moment, not many people have woken up to it. It's not something that you find gazillions of text, this O'Reilly books and Manning books talking about it yet. Right? Though they're beginning to get into this space. And it's very fertile, very new, and if you use it in your workplace, you do have a certain and very distinct advantage. Right? Some of these are very easy to use, so we should do that. Let's plan. And so, guys, share these resources. Huh? Like for me, it was educational to be shown Newton that Kate brought and this Auto ML0 that Praveen pointed out. Right? It was quite the thing. And I literally sat down and did my due diligence on that in the last couple of days. And I learned something. So this particular topic is such that we can all learn from each other. And I can explain you the foundational theory, which I am strong in, but I can't keep track of all the emerging libraries and projects in this space. Okay? So let us help each other out on this. Make it a collaborative effort. With that said, are you guys seeing my screen?
Yes.
Okay. So what I will do now is I will quickly review the theory and want to give much of the time to the practice. But I think that as I could see, the theory has been a little bit confusing for people who don't have a background in Bayesian thinking and so on and so forth. So let us recap what we did and let's finish the discussion we were doing the last time. So if you have been doing ML100, 200, and you have been reading any of these O'Reilly Manning books, you must have heard or seen these techniques, grid search. And most of the people recommend grid search. Interviews, they ask you, how would you do the best hyperparameter search? And you are supposed to dutifully answer that you'll do a grid search across the hyperparameter space. Grid, grid search was the standard for quite some time till somebody realized that actually, if you instead of grid search, you do a randomized search. You just take, if you have a budget for, let's say, 25 points, instead of picking, and let's say that you have two hyperparameters, H1 and H2, instead of creating a grid of 5 by 5 values, right, creating 25 values. So 5 by, this should be 5 by 5, 25 values. Instead, it is much better to take random points, right? Because random points will search the space better, especially if one of the hyperparameters, the loss function is rather insensitive to, the objective function is insensitive to. Right. So then what will happen is if you do grid search, and let's say H, one of the hyperparameters doesn't matter, then you have searched only 5 hyperparameter values for the one that really matters. But if you do randomized search, you will end up picking 25 values for each of the hyperparameters. Right. And so you have a richer coverage of the hyperparameter space. So this is what we discuss. And then let me just review, what, just in case we have forgotten. I keep speaking of the hyperparameter space. First of all, how does hyperparameter differ from parameters? So let's say that you have a neural network, right? Many of these. So this is it. So the weights and biases, the weights here, biases in this, these are the, what are these? Are these the hyperparameters, guys?
Parameters.
These are parameters. And how do you
Parameters.
find the optimal value of the parameters, the model parameters?
Back propagation.
Excellent, yes. So the good thing with that is we can use first order methods and maybe up to a little bit of second order for doing optimizer. We covered this on Sunday, the various kinds of optimizer. That we looked at the second moment and so on and so forth. Not second order, but the second moment and a gradient and gradient square and so forth. So at the end of the day, you can use all of that to create an optimizer, which is some variant of this, some variant of W next is the value of W minus alpha, the grad of the loss function. Now, this is the base or the simple vanilla version, and then you complicate it for Adam and RMS prop, and you throw in more, like for example, you throw in the momentum base or exponential smoothing.
As if you used the term Adam earlier also. Okay. Can you just give maybe
Yeah,
a few
right. Let me do that. Exponential smoothing momentum. See, on Sunday we talked about the fact that you can do exponential smoothing so that suppose you have a loss surface like this. If you just follow the gradient from mini batch, your journey will be very erratic. Well, I'm sure I'm making some weird mistakes, but it sort of is oscillating a lot. When you apply were you there on Sunday?
Yeah, I got the smoothing effect, all that.
Yeah, so it will
The
just
term
create.
Adam, I don't recall that.
So what happens is when you take in smoothing, there are a couple of ideas that come in. One is that you need to do the smoothing, which is through exponential smoothing, right? Or momentum. You apply a bit of momentum. Means you have a certain momentum in a direction. Even if you're being pointed to another direction, you make a slight shift in that direction, but not too much. You listen only a little bit. Then you have to do a little bit of a bias correction. Right? Remember that if you have a lot of points, and you in the beginning it will start low, and so to lift it up and do these are all implementation details. It doesn't, from a conceptual perspective, it doesn't really matter. Then you also the RMS prop, and Jeffrey Hinton, the great Jeffrey Hinton, I suppose, in one of his courses, actually, he surprised everyone by releasing a new idea to improve the optimizers. But he, instead of in a paper, he just casually mentioned it in one of his courses that he was teaching. Prop, which also looks at delta L square. No? It looks at the second moment. It's called the second moment in the language of physics and so forth. Is it this? And then somebody said that, hey, we are doing, this is a good idea and this is a good idea. And what happens if we do a 2 plus 3? Put all the good ideas together to create one big optimizer that benefits from everything. And that became Adam, right? So what it stands for, I suppose, is adaptive momentum or something like that. Right? Momentum, I think. Not quite sure. So this is it. And then Atom is no more the state of the art. Now the latest is Atom W. And then that also may not be the state of the art. The thing is moving forward. And then we come to the world, which we covered on Sunday, of learned optimizers. We're saying that why bother hand creating these optimizers? Learn the best optimizer. And that is still in its infancy, optimizers. Right? Let's learn it as create a neural network to learn the best optimizer function. Right? Because ultimately, if you look at it, W next is some function. If you write it as W minus, even in the simplest form, it is some function of W alpha gradient of L, right? And then you generalize from that. You say that, well, suppose I throw in the second term also, it would be F is a function of W alpha, right? Gradient of L and gradient of L squared, and of course the loss itself. Let's throw in the loss itself. And by the way, there is also a beta. When you bring in the RMS prop, you'll realize that somewhere in there is a beta also that comes in. One more hyperparameter comes in. Actually, hyperparameter, this is the momentum term. Momentum methods. They all have one more hyperparameter called alpha. Beta, this is your learning rate. Right. So this is basically a very quick summary of the optimizers.
And the F's supposed to be included in the parentheses with everything
Oh,
else?
no. It is indeed not. Thank you for pointing that out. F is a function. I'm saying F is some very complicated and unknown function of all of this, right? So we are in the business of discovering unknown functions or approximating it using the neural network, isn't it? So now the thinking is, why handcraft those optimizers? Why not treat the optimizer as an unknown function of all of these inputs and use these to now discover or learn the best F, right? And that is the world, that is the latest and greatest. I mean, I wouldn't call it greatest, is the bleeding edge of research that let's have learned optimizers. And obviously success is very mixed at this moment. Like it is, you wouldn't, let's say that it's a great promising idea, that's work in progress. So Sanjay, does that answer your question?
Yes, thank you.
That's right. All right, guys. So we go back and we ask ourselves that if grid search is like, if somebody, like, let's put it this way, if we say grid search is the right way, we are literally wearing a cap on our head saying, I am a dinosaur, I'm obsolete, right? A better idea is, let's say, randomized search, right? Which is again good, let's say, but what can be better than that? So that brings us to this world of hyperparameter optimization. The basic idea of hyperparameter optimization comes, or the core, the heart of it. I mean, there are many methods of doing hyperparameter optimization. One is, for example, randomized search. You are doing that. But we are going to take a much more nuanced approach. And it turns out that when you don't have a gradient to do gradient descent on, so let's ask that question again. So I'm going to summarize it again in simple forms. See, guys, what happens is that for parameters, you can do gradient descent. Right? Because you know gradient of the loss. But for hyperparameters, what do you do? Right? Because you don't have a gradient of the learning, the loss, with respect to the hyperparameters of the model. Are we together? In fact, it doesn't make sense. So suppose if one of the hyperparameters is which particular algorithm itself to choose, or how many layers to have in your neural net, you can't really get a gradient. Gradient simply doesn't exist of the loss function with respect to this. Like there is no concept of gradient of the loss function with respect to which of the algorithms you picked, random forest versus decision tree versus SVM versus CNN versus feed forward network and so on and so forth. Right? There is no such concept. So what do? This is where the wonderful, wonderful world of Bayesian learning comes in. Now, those of you who have been with me in the math class, of course, I have given you, we did all of this little interesting experiments. Why did this show up suddenly? We did this interesting experiments where we, I don't know if you guys remembered. I gave you a target. I gave you something. I think a ball on a thing, and I said, "Go hit it." Do you guys remember? Right?
Yes.
From a distance of about 20 feet on the stage, you had to throw and try to hit it. How many of you remember that experiment in class?
I do.
I remember that.
You guys do, right? It was fun. So very literally what we saw is that before you did that, you all had a guess on how often you'll be able to hit the target, how easy it will be, right? You started with a prior probability. So some of you felt pretty confident. "Oh, yeah, you'll be 80% of the time I'll be able to hit the target." And then as you did more and more trials, and then you realized that it was actually quite a bit harder to hit the target, you came to a posterior belief that the probability or the proportion of times you can hit the target is much, much lower. And so we went through this a process of learning, right? That is Bayesian learning, in which every time you throw and you hit it, you say that my probability goes up. Every time you miss it, you say that my probability goes down, right? And so gradually you come to the right with enough number of trials, you come to the right probability, that is the actual posterior probability that you will hit it, a realistic. And the interesting point there is you could all have started from very different prior beliefs. Somebody is optimistic, somebody is pessimistic, and so on and so forth. But as you keep throwing, uh, uh, doing your target, trying to hit the target, you converge on a stable posterior, which is the reality. And that is the beauty or the magic of Bayesian learning, that it is the most efficient journey to converge to the right hypothesis of the most optimal posterior hypothesis. Yeah. Given data, each data point helps you learn. And how did we do that? I'll just review that concept very, very quickly. Yesterday I took a day before, I took the example that let us say that magically you have ended up, and I'll now take three cases instead of four, or maybe three, four cases. Rainiest place, number one. The other two is mostly rainy. Three is sparsely rainy. Or mostly rainy, mostly, let's just say uh, medium, half, half, something like that. Four is mostly sunny, and five is desert. right? I believe we took this to be California, this to be Arizona, or something like that. So what we are saying is mostly Rini is saying the prior probability is equal to 1 probability of rain. Remember, I used pi for prior. And mostly rainy is, let us say that I set it to 0.9. Medium, let's say to be 0.5% chance. Half the days it rains. Mostly sunny is, let's say, 0.1. And desert is mostly like prior probability is 0, isn't it? So this is your prior probability values. Right? Now what happens? Now you start seeing evidence. You, as part of your, I believe we concocted the story that you have just been put onto a plane and you have landed somewhere in the witness protection, and you have no idea where you are. So the first day you notice that, so let's say that the evidence says 10 days of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say first day you have rain, sunny. Let's say rain, 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 sunny. And we can throw in maybe rain, sunny, right? Rain, or sunny rain, or let me just put it, no particular reason. I'm just putting in random values. I wish if you were doing it in a Jupyter notebook, we would let it generate the random values with a certain posterior probability. So let us say that this is the evidence you are seeing, right? So tell me, the first day it rains, what happens to your 5 hypotheses? Which of the hypotheses won't survive? So if the likelihood on the first day, L1, is it rained, so how likely is the desert to produce that outcome? What is the probability that you'll see rain in a desert?
0.
0.
0.
What is the probability that, what was the like if this hypothesis is traced, mostly sunny, what is the likelihood of seeing this particular day of evidence? Well, it is just 0.1. This is 0.5, 0.9, and this is 1. So already you notice something interesting has happened. When you multiply these two, you'll get numbers which are in a way, and when you normalize it. So what you do is, let me take you through one step. Huh? You multiply this. So this is the posterior of 1, first day posterior. 1 times 1 is this. So let me call it unnormalized posterior. 0.81, 0.25, 0.01, right? And this is 0. When I add up all of these unnormalized posteriors, so this is what I call the bias box, right? Think of it as a toolbox. Plumbers use their wrenches and other things, and Bayesians use their bias toolbox to get to the right answer. So you can add up all of these. Anybody can quickly give me the answer? One of you, could you please do it on the calculator and tell me what it is? 0.6, 2.06, 2.07. Is it correct? Like my answer says is 2.07.
Yes, that's right.
That's right. And now tell me, guys, that if I multiply, or what I do is I take each of these probabilities and well, okay, I'll just let it be here for the time being. You get an unnormalized a posterior probability like that. The way to normalize it is just to add it up and divide it by, so that all the numbers add up to 1, right? So for example, if I divide this will be approximately half, right? Posterior P1 will be, it is likely a little bit greater than half. It will be a little bit less than, maybe let's say that this is 0.55, 0.52. Is this reasonable? This will be approximately 0.4. This will be approximately 0.16. This will be like vanishingly small, 1 out of 100, 0.005. I mean, I'm just doing rough calculations in my mind. If one of you have a calculator, you can quickly verify whether I hit the right ballpark or not. Does this look okay? If I divide each of these numbers by 2.07, will I get that posterior?
Yeah, roughly, sir. But first one should be little less than half.
Oh, yes, yes, you're right, actually. Absolutely. Thank you. It should not be more than half. It should be little less than half. Let's say 4.8, 4.9, actually.
Actually,
Do
4.8.
it, actually. One of you, could you just do it on the calculator and tell me?
It's 4.8.
Come again?
0.48. 0.48.
0.48, okay. 0.48. So there we are. So guys, now think about it. What is it saying? It is saying that you have 50% likely, that 48% chance that you're in the rainiest place, 40% chance that you're in the mostly rainy place, right? And okay, actually the way to do this was likelihood. No, I multiplied it wrong, guys. See, in the beginning, the probability that any of these happen is 1/5. Oh, that is a screw up, big screw up. See, in the beginning, your prior was, prior is not this. Prior. Hypothesis is 0, is 1. Hypothesis is 0.9. So these are your prior hypotheses. The prior probabilities of this, all of these are the same. So let's do the calculation again. I screwed it up. I apologize. So can somebody do this calculation for me? This is what happens when you try to do everything in as we talk. So this is 0.45. This is 0.25. This is 0.05. And this is 0.
Asif,
Yes.
just a small suggestion.
Yeah.
When you're putting the Bayesian box, this could be a very handy tool. Can you please name the label of the columns properly? So when we revisit the box, look at
Okay, you want me to draw it out in a big way, huh? Let me do that. Anyway, I made some mistakes here. Let's do that. Sorry for wasting time, guys, with this mistake that I made.
No worries, but just think this is very powerful stuff, and we will forget if we don't remember it properly.
Rainy place, right? So, guys, I'm giving you a crash course on Bayesian thinking with an example, mostly rainy. Let's say H3 is medium rainy. Right? So the values you put is P is equal to 1.0. P is equal to, what is it? 0.9. P is equal to 0.5. Let's say that these are hypotheses. H3, H4 is mostly sunny. H5 is desert. Desert. Probability is 0.0. Like P is equal to 0.0. So what you do is you do this, and let me draw it in huge, big things so that we go through this exercise. And if you see this, you'll see why. When you can't do gradient descent, your best option is to do Bayesian optimization, and why it has created a whole revolution here, H1. So I'll just write H1, H2, H3, H4, H5. The prior probability of each of this is 1/5. When you don't have any information, you could have landed in any one of these 5 places. Would you agree? Like your plane just landed and you have no clue. And you are told that you are in one of these 5 places. So how would you spread your belief? You would spread your belief equally amongst the 5 hypotheses, isn't it? For all you know, you might be in a desert. For all you know, you might be in a rainforest.
Correct.
Right? So 1/5, 1/5, 1/5, 1/5. And guys, you guys can help me. If one of you quickly open up a Python notebook, you can do these little calculations for me that will expedite our work. So let's say that the evidence that we saw was this. The first day it rained. Let me put the evidence back up again. Rain, sunny, rain, rain, rain. Okay, let me put it here. Evidence is data is also called the evidence. rain, sunny, rain, rain, sunny, rain, sunny, sunny, rain. Right. So this is our evidence that we are going to work with. So let us not look at the whole data. Let's say that only this data became available to you. Right. First day it rained. So now let's do the likelihood of just one day. What is it? The first day likelihood is, what is the likelihood of seeing rain in a place where your prior probability, like your a prior probability was a p is equal to 1. Guaranteed to have rain, right? Are we together? Here p is equal
Yes.
to 1, right? So what happens now is that you are in a place which is very likely to have happened. This again, actually those values that we did were not way off. I think I lost it. If there is a 90% chance of rain, this is it. If there is a 50% of chance of rain, 1, and the chances of seeing rain here at all is 0. So this hypothesis seems to be already about to be thrown off, isn't it? So we do something called unnormalized posterior, it is called. It is just a calculation step I'm giving you. What you do is multiply these two. So this will become 0.25, or 0.20, 1/5, sorry, 20. Can somebody tell me what this will come to? 0.18, right? And 1/10 is 0.1. Is this correct?
Yes.
Right. And this would be
0.02.
come again.
0.02.
0.02, and this would be 0. So let us go add it up. 20 plus 18 is 38. 38 plus 10 is 48. 48 plus 2 is 50. 0.50, right? Now divide each of these numbers with this. So 20 over 50 is 40%, 0.4. 18 over 50 is the same as 36 over 100. 10 over 50 is the same as 20. And this is 0.4. And this is 0. So your hypothesis, H1, so you say that in view of just the first data's evidence, my posterior probability, posterior on day 1, is already something different. You're saying I have a 40% chance of being in Seattle, in the rainiest place, 36% chance of being here. So what has happened, guys? Do you notice that this number, initially it was just 1/5, 1/5, it was 0.2. This number has increased or decreased, the first one, the rainiest place?
Increased.
From 1/5, from 1/5, it has increased, right? 0.2. This has also increased. This has remained the same at this moment. This has decreased. This has really decreased. So if you think of probability, unit probability as one bucket of sand, initially the sand was distributed amongst all the 5 hypotheses. But now what has happened? This place has lost all the sand. This place has mostly lost most of its sand. And already the sand is, evidence is decking in favor of the upstairs thing. Are we together?
Yes.
Now let's say next day it turns out, oh goodness, it was sunny. So the moment it was sunny, what is the likelihood? Let's look at the L2. And now we will treat this as your prior, let's say, just for the sake of argument, right? What is the likelihood that you would see a sunny day in the rainiest, in a place where it rains every day? Likelihood is 0?
Yeah.
Does that make sense, guys?
Yes.
Likelihood of seeing a sunny day where it rains 90% of the time is 0.1, right? Likelihood of seeing a sunny day in a place where it rains half and half is still 0.5, remains half. the likelihood of seeing a sunny day in a place where it rains only 10% of the time is 0.9, and this one is 0 already. So this is already out of the game, right? So H5 has already gone out of the window. Now let's look at the unnormalized posterior after day 2. How are things looking like it? Multiply these two, you get 0.4. Multiply this with point, you get what? 0.036, is this correct? And
Asif, for the first one, should it be 0?
Oh, I am sorry. Absolutely, absolutely. Thank you for correcting that. That's a big deal, actually. It becomes 0. And that is the main point we are coming to. This becomes 0.1. And now what happens to this guy? What is 9, 0? Can somebody tell me the answer to that? 36.
0.036.
0.036 or 0036?
No, 0.036.
Come again?
0.036.
0.036, right? So this makes sense. Evidence is equally balanced. Now if you look at the total of this, it is like 100 plus 72, 0.172. So let us divide this. So now this is your posterior belief after 2 days of evidence. So tell me, guys, what is 0.036 divided by this? Can somebody quickly do it on the calculator and tell me?
Divided by what?
0.172.
So 0.072.
Is that true? 0.072. What about this guy?
It's 0.209.
That's a point, 0.2.
In the
No,
first
I
one,
don't believe it. If you divide 100 by 172, how can it be that?
first one should be
sorry.
0.21. 0.21. When we
Yeah.
divide
No,
0.06.
that is wrong, Asif. Yeah.
It is totally wrong.
Yeah,
100 divided by
I
172
fixed the
cannot be.
column.
100 divided by 172 is more like 0.6.
0.21 is the first one.
0.21.
H2 yeah, 0.21 is the H2.
Yeah. So yeah, 0.21, 0.58.
0.58 and 0.20.
Again, yeah, 0.21.
0.21. So now look, guys, what has happened. The first one has gone to 0. The last one was already 0, because once you achieve 0, it's not going to get any better, right? So now where has the sand moved? 2 days of evidence, rain, sunny. What seems to be the most likely hypothesis? Which one is winning now?
Medium rain.
The medium one, right? That says half the days are rainy, half the days are sunny. So things are beginning to look different now. 2 hypothesis is gone. Now let us say that you have another 3 days of rain. So maybe I'll bring in 1 more day of rain. Huh? We can do 1 day at a time. Do you see how evidence is getting better and better? Initially, you started with 1/5 probability. Now you're getting 60%, close to 60% sure you are in a medium rain place, right? Let's see what happens if it rains 1 more day. Right?
Asif, for the second day, why did we skip the H5?
Because ultimately the posterior is 0, right? Why bother finding the likelihood when you'll be multiplying it by 0? Suppose you found it out. Huh? Suppose it was sunny. This is 1. The probability of sunny day is likelihood of it is 1. But what is the thing you're multiplying it with? You're multiplying it with 0, isn't it? See, guys, we are multiplying these 2 things, right? These 2 columns. Because this is the new, for day 2, this is the new prior. This is the likelihood. Prior times likelihood will give you what? 0 times 1. Even though there's a very strong likelihood of being a desert because it's sunny, but you have already lost that hypothesis completely.
Correct. Okay, understood.
This is it. So you're seeing how the sand is getting compacted, guys. You know, you started with uniform probability and already it's becoming like, what is it becoming like? Would you say that it's become like this of the 5 days? 1,
Yeah.
2, 3, 4, 5. Look at the 5 hypotheses. Is this the probability distribution
Yes.
looking like? And so you see how your belief shifts and changes. You can bring in another. So now let's do something more. We have another day of rain, right? At this moment, the half and half is looking strong. Actually, because it's getting tedious, can I do 2, 3 days together at the same time?
Mhm.
Let me at least do 2 more days together. Huh? Let me, just for the fun of it. Rain, rain. So in the first hypothesis, the hypothesis 2, probability of rain is 90. So it will be 0.9 times 0.9 is 0.81 likelihood. This is half and half, right? Half times half will be 0.25 likelihood, L2. And this would be rain, rain would be this would be 0.1 times, what is 0.1 is 0.01, and this is gone. We don't even bother about it. Now we can add this up. 81 plus 25 is 106. 106 plus 1 is 107, right? So 1.07. Now we need to divide this numbers by, so what is the unnormalized posterior, UP2? Tell
It
me,
is
guys.
UP3, right, sir?
Come again?
L3. It should be L3, right?
Say that again.
It is L3, right? Day 3.
Oh, right, right. You're right. L3. Thank you. Thank you. So now tell me which is the unnormalized posterior. Normalize it. The unnormalized posterior likelihood, first of all, unnormalized posterior. Multiply these two guys. This needs calculator. Please do that for me.
0.76.
0.76. What about 0.58 times 0.25?
0.23.
And what is 0.21 times 0.01?
0.01.
That can't be right.
Yeah, I mean, like
0021.
0.
Oh, I got the H2 as 0.16.
it has to be very close to 0.01.
This one, right? So guys, what is
It is 0.01.
0.01? Huh?
Yeah.
But how is it ending with 1 instead of 2?
It should be 0.16, right? The first one, the H2.
21.
No, it has to end with 0.01 to make it all equal to 1, right? Summation goes to 1.
Yeah, isn't it 0.002?
Yes.
No, no, don't, you cannot have the summation. Don't guess, guys. Compute exactly and tell me.
Yeah, well,
Isn't it this?
0.009 actually.
0.1 is 0021.
Guys, at this moment, I don't think I can trust any of the calculations you guys are coming up with. So what we'll have to do is open up a Jupyter notebook and do the computation, it seems.
Asif, the denominator is 1 actually. So it should be very close to 0.01. Actually, it's 0.009.
Okay, guys, are you understanding what I'm saying? This is 1.07, right? I'm dividing each of these values by 1.07. So yeah, so all right. So this is now likely, no, sorry, not this. I am just multiplying these two together. 0.21 times 0.81 is what? 0.76. What is 0.58 times?
I made a mistake. Yeah, instead of multiplying, I did the normalization.
Yeah, that's why it's not. So what is 0.58 times 0.225? It cannot be 0.23. It defies belief.
On the multiplication, all the numbers are wrong then.
Yeah, these are wrong numbers. So can you please multiply these two and tell me what it comes to?
Yeah, 1/4 of that is.
It should be around 0.14 or 145.
0.58 times 0.25 is 0.145.
That is it. That's more believable. 145.
So Asif, the above one is like 0.16. And the fourth one is
Third one. You mean the third one?
Fourth, right? Like H1 is 0, and so H4.
Oh, yeah. From that perspective, yeah.
Okay. Yeah.
So
H4 is 0.002.
Yeah, that's what I've been saying. 002. Now add up these three numbers. What do we come up with? The total.
0.3169.
3169. And now tell me what is the posterior belief after the third day. Divide each of these numbers
Yeah,
by
so
the denominator.
0.534
0.534
4 and then 0.458
458.
and then 0.006.
Yeah. So guys, do you notice that this one is 0, this one is 0, and this is on its way to 0? The hypothesis 4 is getting rather shaky because we have 3 days of rain, 1 day of sunny. It doesn't look like a mostly dry place. It doesn't seem that we are in California, isn't it? And now something else has happened. Compare, I'll ask you to compare posterior P2 versus posterior P3. What has happened? Hypothesis 2 is now beginning to lead, isn't it?
Yes.
Right? With 1 more day of rain, hypothesis, yeah, 2 more days of rain, hypothesis now 2 is beginning to lead, hypothesis 3 is beginning to fall behind, and hypothesis 4 is pretty much on life support now, right, at this particular moment. And so do you see, and does it agree with your belief? If you saw this data, is this how you would spread the belief? You would say that hypothesis 2 is more likely than hypothesis 3, right? Hypothesis 1 and 5 are dead. Hypothesis 4 is mostly dead. And what happens if I add 1 more day of rain? Then this will keep on increasing. The next day, we had another day of rain. So do you see how Bayesian works, guys? You just take the evidence. You start with any prior you want. But as you work your way through the data, now what happens to your probability? So now this is your day 2, P2. Now, what does P3 look like? Where is it? P3 now looks like what? P3 looks like this is dead, this is dead. One of them is practically nothing. No, hypothesis 2 is winning, it's more than half. Hypothesis 3 is lagging behind. Hypothesis 4 is almost disappeared. And hypothesis 5, 2, 3, actually 4 is almost close to 0. Very hard to tell that this is not 0. And this is 4, hypothesis 5. Do you see, guys, how your probabilities have changed? Posterior probabilities have changed. And does this make sense? And that the only viable situation looking at this data is either it's very rainy or it is medium rainy. Guys, I hope you're seeing that this is very intuitive.
Yes.
It
Yes,
is.
Rafi.
This is it. And you can play this game more and more. And ultimately what will happen is it will gravitate. It will now keep oscillating and it will equilibrate at the right solution. But what do you notice? A flat distribution like this. Like this. P, and this is 0.2. All the hypotheses, 1, 2, 3, 4, 5, initially you had equal belief in them. Now you have already abandoned belief in 3 of them, more or less. And now you'll see more evidence. So what happens to your understanding of the situation? You begin to have a better and better understanding of where you are. Would you agree, guys? And that is Bayesian reasoning. Huh? That is the gist of Bayesian reasoning. That's why Bayesian is so important. We are all Bayesians. We just don't know it. We reason like this, right? When you say from experience I've learned, then if you learn something correctly, then you have learned it the Bayesian route.
Asif, if different people have different priors, they would still arrive with all the evidences and the likelihoods. They will all arrive.
Do you want to try that? Do you want to try that experiment?
Oh no, it just occurred in my mind to.
Yeah, it is. So suppose I'll let you do this. So suppose you have a strong bias that I must have landed up in the desert, right? So let us say that you start with hypothesis 1 probability, 1, 2, 3, 4, or 5. let's say that your hypothesis one that you are in the rainy place is very little and never set any value to 0. Let me just say 0.0001, right? Hypothesis two that you are in a very rainy place is also low. Let's say 0.1, 10%. Hypothesis two that you are in a very low place is all, I mean, medium rainy place is also very low. And your belief that you are in a mostly rainy place, mostly dry place is a little bit more, maybe let's say 0.2. And let's say that your belief that you are in the desert is like, okay, if I want to add all of them, it's like 49999, something like this, right? You can start with this prior, but what will the data do to you? Do you want to play this game again with this kind of a prior? You will notice that you will essentially start coming back to this. You will take a little bit longer to come to the answer, right? But you will get to the same answer after you have seen enough data.
I see.
Right? And that is the magical thing. Just think about it for a moment. It doesn't matter if you're wrong in the beginning. So long as you're willing to learn from data, from experience, you will come to essentially the same truth, the same posterior belief. Do you see how lovely it is? Right? And just some very elementary mathematics.
So Asif, it is good to start with a randomized prior in to arrive at the conclusion faster.
No, you don't. You don't. I'll give you an example. See what happens with a random, completely uniform prior, like equal belief in all the hypotheses.
Oh, equal belief is what I was about to say.
Equal belief. When you start with equal belief, you call it. There's a word for it. It is non-informative prior. Non-informative prior. What you're saying is, I really don't have any hunch, right? So I have no reason to believe one hypothesis more than another. So my belief is equally spread amongst these. But usually what happens is that you come with some belief. So I'll give you an example. Suppose you have to get a surgery done, right? And it's a risky surgery, open heart surgery or something like that, or some very risky surgery. You are going to a person in a hospital which is poorly equipped, and there is a very young resident standing there, right, with his knife in hand, and asking you to come into his operating theater and he'll act on you. At that moment, and then there is another doctor, let's say at another hospital, let's say UCSF, and he's also a cardiologist, a heart surgeon, and he's like old, is 45 years old, has 20 years experience of surgery, and he's also holding a knife in hand. Now, before any other evidence happens, like whether you go under anesthesia or so on and so forth, suppose you had to guess, a prior probability guess. What is the probability that you'll come back alive under the first case versus the probability that you'll come back alive under the second case? Would you assign the same probabilities?
No.
No. Your prior is therefore informed. You have a hunch. You know something that the math doesn't. And so that which you know before you see the data, it is your prior experience. That's why the word prior is used. That which is your prior guess based on experience is your prior. So you give different values to the two hypotheses, the two you give different probabilities, prior probabilities, and then you let the data speak for itself. Right? It is still possible, that surgeon sitting in a top-notch hospital may have blundered through all his patients, and that's what the data will show. Right? And that young resident sitting in that poorly equipped hospital is actually brilliant at surgery, and you just didn't know that. When you see the data, your belief may shift. But before that, just looking at the two situations, you come up with a prior belief in which you give more importance to one versus the other. Right? So guys, this is a detour I took you through Bayesian because the auto ML, the foundation is Bayesian optimization. So it is important to know Bayesian learning. We did a rather little bit fast-paced intro, and of course we didn't go very deep, but I wanted to show you the magic that is Bayesian. How you go, so the way you say this is posterior belief or posterior hypothesis belief is proportional to prior belief modified by, multiplied or modified by likelihood of data, likelihood of evidence. How likely is this evidence? How likely is your hypothesis to produce this evidence? That is what we did. Remember the L, and we multiplied it. So when you just keep it as a proportionality, you're looking at the unnormalized posterior. And if you want to do that, then you have to divide it by the sum of all, sigma of all, to make it a complete probability. So this is the heart of Bayesian learning. That you take a prior belief, no matter what, but so long as you are willing to learn, this is the learning part. You are coming to a posterior, right? So now let us bring it back to our world. How does it relate now to what we are doing? Oh goodness, today is becoming more a theory session than lab. Guys, I do want to do the lab. So can we extend this session today? Can we do it like, let's say till
Yes.
10:30?
Yeah.
You can do till 10.
Till 10, not 10:30, huh? Okay.
10:30 is.
Yeah, I think 10 would be good.
Yeah, we have scheduled call.
Okay, guys, so maybe we'll break it up into, I'll cover the rest of it in the future. But so now let's go back to it. See, you have a hyperparameter space, H1, H2, hyperparameters, H3. Hi is the hyperparameters. Oh, this is a bad spelling. Hyperparameters. Now, the Hi. Now, let us say that, for example, H1 could be the learning rate. H2 could be quite literally layers in the, how many layers in the network? Layers count, right? H3 could be your regularization parameter. Something like that. It doesn't matter. Huh? So you can keep going down. Now you realize that in this vast space, actually, I just screwed myself. I made it a three-dimensional object. And it's hard for me to now on a two-dimensional place make it. So let me chop off one. But you should assume that there are many, many hyperparameters, huh? H1 and H2. I'll just keep it to this too, so that, you know, we can draw. For each point of the hyperparameter space, any point you take, it is a combination of H1, H2, any point X is a combination of some value of hyperparameter 1 and hyperparameter 2. Would you agree? Isn't it?
Yes.
Right. So now comes the very simple argument. Now that you understand Bayesian, this entire reasoning will become very clear. So let the evidence be D. Evidence or data be D. So think MNIST, for example. MNIST is there, right? Let us say you have an algorithm which has these two hyperparameters. So you do this. For choose a hyperparameter, choose X randomly or carefully or whatever, etc. Whatever you make an initial guess of X, optimal X, right? You know that, okay, so now what happens is you have to create an objective function, That's the word we use in this literature, objective function. Objective function is this box, F. X goes in. What is X? It's some combination of hyperparameter 1, hyperparameter 2, goes in. And what comes out is this, the loss that you have, the residual loss for this data set D, residual loss for the data set D given X, right? Given, if you take the MNIST data set, you run it over the validation set if you want, but test set, I won't talk about test set. Let me just call it data. Huh? You find the total loss on the data given this value of X after the training has happened. Means you go through your epochs, go through learning of parameters, right? Or optimizing the parameters, not the hyperparameters. So no matter what you do, see, ultimately the loss that you're left with depends on two parts: how perfectly you fit the parameters and how good hyperparameters you have picked. Now, parameters you can optimize very easily because of your gradient descent and backprop and all the lovely magic, isn't it? If you're doing neural nets, if you're doing support vector machines, whatever it is, you can train it basically. The parameters can be trained, right? And after you have trained it, you would still be left with a residual loss. This is the loss that remains after training. Would you agree? This is the loss you're left with after training, given this hyperparameters. So far, so good, guys?
Yep.
Yeah. So now, with this fact being there, and now the statement is that, see, guys, what the problem is, this objective function is unknown. You know that in some sense, the loss is given the data and given this hyperparameter is, and we write it as y, is some unknown function of x. Some unknown function of x. Now what happens? If it is unknown, how in the world do you discover it? You can't, can you? If I tell you that there is some very complicated and unknown function of x, now go guess it. What will you do? But by the way, here is the data and you have to guess it. What will you do? There are only two things you can do. You can keep taking a lot of values of x and seeing what y comes out. And from that, you may start noticing some pattern, isn't it? Are we together? So let us do that. Let us say y. And if you don't mind, I will just make x as a one-dimensional thing at this moment, even though it is two-dimensional. But imagine that at some point. So what happens is that, suppose I pick, actually, why pick that? Okay, maybe I'll do that. Suppose there is you pick a point here. You find that the loss is this much for this value of x1. You take another point here. And you take, I don't know, another point. Where should I take it? Maybe here. It's like this. I'll just take 3 points. And now you know the y values. You don't know f. F is an unknown function. But what are you tempted to do? Tell me, what would you be tempted to do? Just looking at these points.
Continuous. Try to connect all of them.
You try to connect it, right? So what you do is, so for example, if you make a smooth curve, something like this, you may be tempted to do this, right? You may be tempted to do this. You may be tempted to do this. All of these are going through these points, isn't it? Any one of these lines could be your guess. You know, these guesses that we make, what we do is we create something called surrogate function. Surrogate function. Right? And the word surrogate comes from surrogate motherhood. You know, let's say that you can have a child, not necessarily from the true genetic mother, but the child can be born from a surrogate mother, isn't it? For example, It's sort of somewhat similar interest. So what you're saying is we can actually, instead of trying to find the minima of this, because the problem you're trying to solve is the best value of the hyperparameter is the argmin of x, that value of x that minimizes the function fx, except that you have no way to minimize. Calculus is out of the window, isn't it? There is no gradient. So forget about doing gradient descent. We still have to solve this problem. So what you do is you start making guesses like this. These surrogate functions you start creating, right? So let me just call the surrogate function Sx, right? And these are simpler. You deliberately choose simple, nice, smooth functions. Do you see this, right? But there is a problem. There are so many of these functions you can fit through 2 points, right? So one way you can think is you're trying to put a polynomial through this as an example. Huh? I mean, usually you do it slightly differently, but one example. Huh? You can do it, or you can throw some Gaussian mixtures, so whatever it is you can do. Now what happens is another data point comes in. Let us say a data point comes in like, so when you look at this, right? So let me actually color it differently, guys. To bring home the point, I'll just do it differently. I think I should have thought of these diagrams more. So let us say that one hypothesis says this. Another hypothesis says, what is it? This. Another hypothesis says, what should it say? Maybe it has to go through these 3 points. So it may say this. You see, oh, sorry, I should use a different color. My bad. 1 second. Let me use some other color. Yeah. So I'm just making some giving you guys an intuition, guys. So all we know is that these 3 points exist for which we know the loss. Now we can fit in a lot of these lines through it, curves through it, functions through it. Now what happens is that you can now distribute your belief or faith in these 3 lines asymmetrically. Like you may have more faith in maybe the yellow line, maybe you have reason to believe the red line, or you have some reason to believe the green line. You can do that, guys, isn't it? You can choose to have asymmetric belief in the 3 colored curves, the 3 surrogate functions. Would you agree?
Yep.
Right. Now what you do is, it's all right. Then you bring in, this by the way, these functions, because they create curve in higher dimension, as you can imagine, it's a surface. In fact, in our problem of H1, H2 itself, because it's a 3-dimensional problem, it's a surface. The word for this is also response surface. Response surface. So now what it is saying is, guess what? Looking at these hypotheses, if I have to find the next point where I should do what is a good candidate where I should train the algorithm again and see what loss I get, apply the objective function to. What would be a good candidate? Looking at this, what would you say? Where would you put it, guys? If I ask you to pick a point, that combination of the hyperparameters where you want to test for a good loss, low loss, which point would you pick looking at this data?
I pick something beyond that range to get a better feel for the shape.
You mean something here?
Yeah, that or the 0 point or more points. It's not enough points with only 3.
Right. So see, one thing you could do is you can say that, these response surfaces, they seem to imply that this seems to be the neighborhood which looks promising based on the 3 curves we drew, isn't it? At this moment. So, and your point that you made is, let's just look it up at some other point, let's say here, so that will help us choose between the green, the yellow, and the red. Right. And those are the 2 approaches. They are called, and this is a classic, ideas coming from reinforcement learning and so on and so forth, algorithms. We'll talk about it. See, guys, the theory here is very elegant. They're all these multi-arm bandits and whatnot. We'll talk about, which I haven't taught you, so we won't get into it. But you do a trade-off between two things. A trade-off, between two things. Exploitation versus exploration, right? So what happens is when you say, let us pick the next point in something that looks promising, right? And suppose you pick the next point here. Let me take an example, A. You have gone in favor of already picking a good point in view of your exploitation. You're exploiting the knowledge you have so far. Exploration is saying, hey, you know what? Maybe we should search the rest of the hypothesis space and see what's happening there. So that we don't, we don't know what's happening here, all of these places. So let's go and explore more of the hypothesis space. And suppose you pick a point, let's say that you pick a point, I won't take this. Suppose you pick a point, you're trying to determine what value there is, I don't know, someplace here. Let me just take B. Right?
Yeah, what if it dips back down? Maybe it's...
It is possible. So what happens is, by the way, these A's and B's are here. This is A, so I shouldn't say that. I should mark, you're right. It's a good point you made. I shouldn't put it here. Ultimately, this is the hypothesis X direction for hypothesis, right? So let's say that you have another hypothesis B, completely far away. At this moment, what is happening? You are beginning to pick, you have points here, points here, points here. And these three values are tempting you to pick A. If you pick A, you're exploiting the likelihood, the likely zones of a good Y. On the other hand, when you say, no, we need to look around a little bit more, let's go to B instead. You're doing exploitation, the exploration. You're saying, let's explore a little bit more, right? To get more feel for how this response surface looks like, or the surrogate function looks like. Do you see the distinction between choosing A versus B, guys? A B, we don't know what the value of Y will be. It could be anything, right? Along this, because there is so much uncertainty. We haven't explored that region at all. But around A, we have picked two things to the left of A, one point to the right of A. So when you go for A, you are actually going for a likely good place. That is exploitation. The opposite of that is exploration. You say, no, let me first go cover my, cover my bases. Let me go and check areas which I have not explored yet in the hypothesis space. Are we together, guys? Do you see why each of these have their pluses and minuses? Tell me, guys, anybody who has not understood it, since no one is responding.
Asif, you are saying there's merit in doing both, right?
Balaji, a little bit closer to the microphone.
Oh, okay. So Asif, you are saying that there is merit in doing both?
Yes, there is merit in doing both, right? See, you may be tempted to go for exploitation. You may be, so I'll make this situation more extreme for you. And then you tell me. So suppose the situation is like this. I go and I really find that A, the Y turns out to be low, right? So now what happens? Your loss, there's a potential, another loss value. What color should I take? Blue. Now you might be tempted to go with this. So now, do you pick this minima, C, right? C, or you pick B anymore? Do you realize that the evidence is beginning to mount more towards C, right?
Mm-hmm. Mm-hmm.
So at that moment, exploitation seems to be the better choice as opposed to exploration. So what you do is you have a function It is called a selection function or a acquisition function. People use different words for it. Acquisition function or a selection function is job. So now we have three things, guys. We talked of the objective function, we talked of the surrogate function or the response surface, and now we are bringing in one more function, the acquisition function. So many more actors, many more cooks are entering your kitchen now and helping you cook up this best model. What does this acquisition function do? It is the one that tells you that given this trade-off, what should be the next point? What should be the next x, xi, h1, x2 to evaluate, right? So good acquisition, and there is a bit of mathematics that people use. I will just mention it, but it's not, that's technical detail. It doesn't matter. There is something called expectation improvement. Like how much expectation you have that your loss function will improve. Yes. And it is given by an integral y star minus y and your current posterior curve. So whatever curve that you have so far, your surrogate function, right? Y given x dx. So this is your surrogate so far. And this is your EI. And what is Y star? Y star is just some reference value. You say, I wish it's a threshold value. You can pick a good threshold value will be the lowest loss that you have observed so far in your experiments. That could be a good. And now you evaluate this, right? And so it turns out that if this turns out positive, you're likely you are moving towards a place where there will be this is dy actually. I shouldn't say x. Why didn't I say x? Right? For this given x, given, so you pick a point based on how much improvement you expect this acquisition function or selection function expects to get by jumping to that point. So there is a bit of mathematics. I won't go into that. By the way, this is the classic formula of expectation of any posterior. Anything, the delta, right? Where to go, and if I go, how much do I expect? These are like, see, let me put it this way. Suppose you have a function px, fx, and the probability, there's a probability distribution this. The expectation value of fx in statistics is called this, right? This is basic statistics and the definition of expectation value. So I don't want to review those statistical concepts at this moment. So just ignore it because we need to do a lab. It's already 8:30, 8:40. So this is it. And so what happens is that you hop around, you use this exploitation versus exploration. And so what happens is that your region of uncertainty, which in the beginning was quite high, let me pick this. Region of uncertainty should be which color? This. No, it hardly shows. No. What color can I take this? Bright. No. Okay, none of this is helping me too much. So let me just mark. Okay, see, here's the thing. Gradually what happens is that sooner or later, let me just mark it here. Suppose this is really true. Hang on, white. Right. And what happens after some time is, and you have done more experiments, one of your guesses would go like this. Another of your guesses may go like this, but they begin to converge. Do you see all those different sort of things that can go through all those points? They begin to look alike. Am I making sense? So let me just say they're going through this here. They're going through like this. They all are converging and beginning to look like this. So what has happened is you have essentially created a good surrogate function by continuously trying to adapt to the data, the few data points you have. You have created a good surrogate function, which is, let's say that ultimately it all begins to approximately look like this. right? And remember that your axes are L versus X. So now all your data seem to fit more and more this surrogate function. What can you conclude from this, guys? Can you find the best hyperparameter combination? Where is it? It is at the minima of this function, isn't it? This yellow function. This is your X star. This X star is argmin min of fx, the actual objective function. Would this be a good answer to that? Are we getting it, guys? So what we did is that we don't know the objective function, but we created a surrogate function, and it seems to fit the trials very well. And we use that surrogate function then to, which we can minimize because it's a function of our choice. It's a nice simple function of our choice. Now we can just apply calculus or whatever, gradient descent or whatever, to the surrogate function and find its minima. And wherever the minima is, we claim that that is our best combination, the best hyperparameter tuning at that moment. Am I making sense, guys? So see, guys, this is a very intricate, a very lovely reasoning. If you're familiar with Bayesian, you look at this thing and you just smile because it is yet another illustration of the power of Bayesian ideas and Bayesian optimization. At this moment is extremely hot for hyperparameter tuning, and it's at the heart of, at this moment, it is at the heart of this whole automated machine learning in which you have models that tune themselves.
So as if the only intuition that's a little hard to grasp on this one is when we think about arriving at the minima for that function, there's a mix of discrete and non-discrete variables, right? Like if you take in the case of a hyperparameter, like a choice of an optimizer.
Ranjit, for the time being, so the discrete is where that tree part of the tree, tree structured parser and estimator comes in. I would say that in the first early stages, just forget the fact that anything is categorical or anything is discrete. Just first get the intuition for continuous hyperparameters.
Okay.
Once you get it, it's a small complication or extension to make your intuition fit with this. Don't worry about that.
Okay.
But if you just assume, like, get the intuition right, just get the intuition with completely continuous functions, right? Hyperparameter values, which are real valued. Yeah.
Okay.
But your point is valid. I didn't take you through that. See, we have limited time, guys. Do you realize that every week we are covering big swaths of, like, literally some subfield of machine learning? Entire subfield we are covering in a week. And yet, this is one of the longest workshops you'll ever go through, 18 weeks. Okay? So we have to move fast, but at the same time, we have to focus only on the core ideas so that other things you can pick up on your own. So far, so good?
Yeah.
Yeah. So therefore, what we did is that we said the objective function is unknown, but we can come up with a surrogate, which is a pretty good approximation that will do the job. Just as a surrogate mom is completely able to do the job, keeping a baby alive and giving birth and so on and so forth. So what happens is that the surrogate model has effectively given birth to the best hyperparameter, right? Which you couldn't have gotten from the original objective function. And the three pieces of the game were objective function, which is literally pick a hyperparameter, compute the loss, do your network training and come out with the best loss. Then the surrogate function, which is your literally surrogate. And then the last is the acquisition function or selection function, which does the exploitation versus exploration trade-off, right? And it uses some expectation value and so forth. So now what happens is, this is the core of Bayesian optimization. There are many implementation details. Yesterday, the day before, I said I would do the parser estimator. Actually, forget, in hindsight, I don't want to go too much into it because we have gone technically deep enough and those implementation details frankly don't matter. So the three leading areas are, one is just do random forest regression, right? So, you see all of these points, just fit a random forest regression model to it to find the best fit model. We can do that. We have done regression, isn't it? That seems like a no-brainer. Another thing popular is, of course, something called Gaussian processes. So when I was making all of those curves, actually, this particular way of explaining goes to the heart of something called Gaussian processes. It's again a subfield of machine learning and very Bayesian, extremely beautiful and deep. Obviously, it's not something that we covered in ML100, 200, or 300, or 400, but I allude to it in our math course. I can give some references. It's lovely, but it's again one of those things you go deeper into if you want to really master Bayesian. Now, it turns out that as this automated machine learning becomes very relevant and central, maybe it's a good time to learn about those. So this kind of reasoning that many curves, each with different belief you have in them or faith you have in them, is a Gaussian process explanation. Then there is the Parson estimator explanation. I'll give you a rough idea. What it takes is that, actually, why bother? Maybe I'll bother. But if you don't get it, because I need to get to the lab, you take a threshold value of y, y star, the one that I was talking about. And then you create a function which is two curves, one Lx, which always does below, one gets greater. And then what you do is you try to, in some sense, converge from this. You sample from this. And there's a bit of explaining to do, some magic happens, Bayesian magic happens. And ultimately, using the same thing, this will optimize itself. Right? The tree part of it comes frankly from what you asked, the discrete part, when you have categorical aspects. Okay. So these three methods, at some point, try to read up on your own. And at the risk of this lab session becoming a pure theory session, I think I should stop. So I'll today take you through two libraries. One uses the Gaussian processes, and the other uses this one, tree structured. People don't use the word tree structured, a Parson estimators, TPE. Everybody calls it TPE. Most people don't remember what TPE stands for. So I will go through libraries in the lab that covers these three. So guys, it's 8:49. Do you guys want to take a 10 minutes break before we come back for an hour of lab?
Yes, please. Is there something for us to download from the portal?
No, unfortunately, I didn't get time to upload anything. So let us do it as we go along. Huh? Oh, by the way, guys, was this explanation useful? Like, did it help clarify your understanding of things? Did you get a core idea of what Bayesian reasoning is and why it works?
It's very useful.
Yes, yes.
Yes, sir.
All right, guys.
The last part, I think we need to get better at it, but the first part, totally.
Yeah. All right, guys. So I'll catch up with you exactly at 9.
Okay, so we'll just open a Jupyter notebook and put stuff in it together?
Yes, I will help you do that.
Okay.
So All right, folks, I hope we are here. Can I assume we are all here, guys? I'll resume the recording. Any response? Anyone?
Yes, Asif.
Okay, all right. All right, guys. So on the portal, in our course portal, you'll see that I have put quite a few resources from a long time ago at the beginning of this course. But this list is obviously we need to augment this list with more and more items. Do you notice that we have a wiki here? If you go to this wiki, guys, each one of you can add content. You can go to the edit and you can start adding new content that you find. And if you can do that, like for example, the Newton dot whatever zero, you could add some resources. I'll really appreciate it. Or if not, then just post it to Slack, and I'll keep adding it to our class page. As I said, this particular topic is moving so fast that the only way we can
Should we be opening?
Say that again. Did somebody say something? No. Okay. So the only way we can make progress is if we collectively.
Can this notebook be anywhere, or do you want it to be in the homework directory structure?
I didn't understand notebook. It is a. Kate, I don't understand your question. What is it about notebook?
Well, we're opening a Jupyter notebook.
Not yet. Not yet. We are not. We're just looking at the web page. So at this particular moment, all I'm saying is that as you guys find resources, either keep adding here or add it to, just put it on Slack and I'll keep adding it to the course portal.
Yeah, Asif, I don't think we have access to add the link.
No, you have access to editing it. Just click on one of you, just click on the wiki. You can't add a link, but you can click on the wiki and then go edit and put things there. Can you click on the wiki, please? You know this participant contribution to AutoML? Could one of you verify whether you are able to click on this? It will take you here. And here you can go to the edit tab and you can start editing, adding things. Could one of you confirm that you guys are able to do that? Any volunteers?
Is that under hands-on lab and solutions, the development environment for AI?
Oh, it's only view only, like for me.
The view option is the edit option is not there.
Yeah, view only, like no edit.
Okay, it's all right. Then let's forget that. I don't know why I couldn't make it editable. I'll see what I can do. Maybe it's a setting. Let me see if I can. Oh yeah, participant. Let me see. So edit settings, permissions. Maybe. What is this? Instruct, delete comments, view comments, create new wiki page. Yes, activity. It seems to be there. Okay, I'll figure it out. Let's not lose time over that. Just post it on Slack and I'll keep adding it to that. But these are some of the links. Now, let's go to the facts. What I will do is, there is a whole wealth of articles and coverage on this topic. But let's start with something that will show sharp work. So,
Asif, can you please increase the font size?
Yes, I will. Better?
Yeah, maybe one more. Yeah.
Okay, hang on. My screen seems to have frozen. Okay. Is it any better?
Yes, this is good.
Let me do one thing, guys. I'll put it on the other screen and share that. For some reason today, Zoom, we just updated Zoom and it doesn't seem to like
Zoom was popping me in and out like 3 or 4 times just now.
Yes. I think the new update to Zoom isn't the best for some reason. So please bear with me for a moment, guys. Let me share a different screen. Stop sharing. and share. We may have more luck with that screen. All right. Not particularly. For some reason, my browser is not cooperating. It will come back up. Yes, it has started cooperating again, but it took a while. I can't. Guys, it's too big a font. I'm not able to see. Can I reduce it a little bit? Or
That's
Yeah.
fine.
it's very
I'm
hard.
sorry if I missed stuff because I was popping in and out of Zoom. Where are we now? Do I open a brand new notebook
No,
and
you
should it
don't.
be in one of
Just
the
follow along. At this
homework
moment, do
10?
not do anything. Just follow along. That's all.
So you can make it
Just
smaller, Asif.
Okay. Okay, I'm just waiting for this thing to respond.
Yeah, it could be smaller.
Yeah.
It's a little
We
overwhelming.
try. Folks. No, I'll have to again go to the. Yeah. Okay, guys, wait. Huh? My browser is simply not responding with this. Ever since we got the new Zoom update today afternoon, things are going pretty badly. Okay. This looks hopeless. All right, let me try another browser. Let me go and get the link here. This is now any luck in getting a different. Okay, let's go to Firefox. Otherwise, guys, I'll move over to the Linux side because I know that in the Linux side there is no problem. We work just fine.
If the notebook is available, as if we can open it also locally.
It is not available on the internet. Oh yeah, I mean, yes, some of these notebooks are available. One of them that's available, I don't know. We will see which. Some I have posted, some I have not. So today I'll start with the first one, SK Optimize. Of course, I'll upload everything in a bit. Yeah, Firefox seems to be behaving better. Now let me try increasing the font. Guys, is it better now?
Yes, sir.
Okay. So guys, remember, I'm not asking you to do anything at this moment. Please don't get busy doing something. Just pay attention. So I'll take to motivate this example, I'll take the obviously MNIST dataset because we can carry this dataset through the different libraries. We know what MNIST is. It's a lot of digits, zero, like handwritten digits, and we have to classify them to be between 0 and 9. So we have done that. In the beginning, we'll just go load the data. Scikit has already the data built in. We can load that data in Scikit. Now, there is no automated machine learning here. What I'm doing is, we realize that when we deal with support vector machines, there are many hyperparameters, support vector classifiers, many hyperparameters. First is the kernel itself. Do we take a linear kernel, a polynomial kernel, a Gaussian kernel, RBF kernel, or what is it? Which kernel do we take? Right. Let us assume that you took a Gaussian kernel. Now still, there are two more hyperparameters. What is the budget, the C, the cost, and the other is the gamma. Remember, e to the minus gamma d, the thing. So what is the gamma? And this is obviously those people who haven't taken ML200 with me may struggle a little bit, but just take it as a fact from me that support vector classifiers have many hyperparameters, two of the most important being the cost and the gamma. Right? And of course, which particular kernel you choose. So by default, it is RBF, the Gaussian kernel, so we'll stick to that. So typically, what you would do is you would instantiate the classifier and you would put a guess of the cost and gamma, isn't it, guys? You would guess some value for it. Am I making sense?
Yes.
You would pick some value. It doesn't matter. Randomly, you would pick some, and then you. And at this moment, we are not doing grid search, right? And so you would run it. The rest of the line should look very easy. SV fit, I hope, looks straightforward. Y hat looks straightforward. This thing looks straightforward, right? You fit the model. You get the predictions. Then you get the classification report. And you seem to be getting variable amount of accuracy. The F1 score varies from 61% to the high of 98% for 3. 3 seems easy to identify. The overall accuracy seems to be 86%. Right. So now you know that that is respectable. What happens if I change the gamma? Let me change the gamma to or let me just play around with it. What if you make the cost to 10, right? And I run this again. Now your accuracy is about 87%, not much change. What happens if I change the gamma to, let's say, 0.1? Right? Oh, now your model has become distinctly bad. Do you see this, guys? Huh? So when you do randomized search, you can put it in a loop and you can try out randomized cross-validation search across different values and so forth. But the whole point of automated machine learning is there a way to use Bayesian optimization and find the best value quickly, right? That is the main point, right? And if you remember, the scikit-learn comes with cross-validations. It comes with grid search CV. It comes with random search CV. These are the two things you're familiar with, guys, isn't it? But now I'm going to introduce you to what this library does. And that's a nice thing about the sklearn, skopt, right? The scikit optimize. The lovely thing about it is that it completely conforms to that naming convention. It is almost as though you don't need to know the whole theory of automated machine learning. Somebody just whispers in your ear and says, hey, don't use random CV, random search CV or a grid search CV. Instead, use bias search CV. Do you see this? Then what you do is in the bias search CV, you set up the parameters like of the hyperparameter search space. See, you say that search in 10 to the -6 to 10 to the +6 in log uniform. Means if you take the log of it, it will go from -6 to +6, right? Log C. So choose it to be from 10 to the 6, 10 to the 5, 10 to the 4, 10 to the 3, 10 to the 2, 10 to the 1, 10 to the 0, 10 to the, and 10 to the -1, all the way to -6. So you're taking about 13 values here. So you're actually scanning a pretty vast range of scales for the good value of C. Likewise for gamma, you're picking values from 10 to the -6 to 10 to the 10, from 10 to the -6 to like 1 millionth to 10. And again, a log uniform space. If you're taking a polynomial kernel, you're taking degrees from 1 to 8, right? 8 possible degrees. And there are 3 kernels. So guys, can you imagine what a large computational space you're looking at? 13 times 7 times 8, 13 times 8 times 8 times 3. Right? If you were doing a grid search, you would be doing a whole lot of computations. Would you agree, guys?
Yes.
Okay. So grid search would be brutal. And then you can do randomized search, that also will be not. Now look at this. This code is exactly like what you do with your scikit-learn. No difference. And so when you do the lab, it's just so easy almost. You might even wonder, why did I teach you automated machine learning? All I could have done is just say, use this instead of whatever else you have been using. But they made it this easy. You fit, and then you come up with the best score. So it says that, look at this. The accuracy now is 98.66 compared to what we were getting. Low values, we are getting in 88. Even with good values, let's say 0.01. we were getting at most 87%, right? So compared to that, in one fell swoop, it has managed to come up with this score quickly. Are we together? And it finished in 26 seconds, 27 seconds, which is pretty impressive that it managed to find the best value. And if you look at the value that it found, you would not have guessed it. Look at it, guys. What do you think about these values? It is saying that two kinds of support vector machines will work, where two kinds of kernels will work. The best we seem to be getting is with polynomial kernel. In the polynomial kernel, you can have the best value that you got was for cost this much, 1.27, and for degree 3, right? And if you use a RBF kernel, it happens to be, the gamma for that happens to be 0.00034. That's that. Is it making sense, guys? Do you see how easy it is to do it?
Yes.
So
Totally easy, isn't it?
the SK opt package, that's also part of scikit-learn?
Yeah, that's right. They are all
Okay.
part of scikit-learn. And so you'll see, and I'll give you, I'll take you through the documentation page in a moment, right? So then you can do it with more. Like, for example, you can say, let me try more things. Let's say that a more detailed example in which I give all sorts of model parameters to search for, make it more and more complicated, and then run it. It will run again. Even a sophisticated run just takes 43 seconds, right? Which is nothing compared to doing a massive grid search. And SVMs are not easy. Now we are using linear SVMs, all sorts of things. And then once again, it comes out with the best model value, right, for the classifier. And now it is coming up with a value of the classifier with all of those things, which is different. I mean, see, the point is that this kind of optimal values you could not have discovered so quickly, either with grid search or randomized search, isn't it? That is the only message here, right? Obviously, if you try to do it on the iris data set, it's too trivial. So it will very, very quickly come to the solution. Right? So that's that. So so this is just one library. Let me now show you something about this library. Now let us hope that
One question.
Go ahead.
So when we are calling this bias search, the parameters that we are giving, the C and gamma, are those fixed, or those can be anything that depending on the
No.
model?
They come. See, here is the thing. Where do these parameters come from? C gamma kernel. Because you're using scikit-learn. So here is what you would do. You would go. We are using scikit-learn's support vector machine, isn't it? So let's go and find scikit-learn, sklearn, SVC, right? Documentation for it. We go to the documentation and see what are the parameters here. Do you see the hyperparameters? C, kernel, degree, gamma. So you have to stick to these names.
I see. Okay.
That is it. That is why they have made it very close integration with that. So now, guys, let me take you to the website of this. Where is the website of sklearn optimize? This is our sklearn code. So there's so many libraries I want to show you. I'm myself feeling a bit, I have that open here. Oh goodness, it's not worth searching for it. So I'll just go and search for sklearn optimize. It's a lovely library. You can go there. So this is the Bayesian search cross-validation. There is a lot more functionality there. I just got you started on this. So please go to this website, look at the examples and look at the user guide. It will take you some time to, master it. But if you look at this website, you can clearly tell that it doesn't rise up to the standard of scikit-learn or PyCharm, PyTorch, and so forth for either maturity or documentation, right? It's sort of work in progress, and that's the nature of all of these libraries. So you can go to this. You can just Google, guys. Can you please Google scikit-learn-optimize and bookmark this page? Okay. So the example that I took is literally this example. You see this example here. I put it in a notebook, which is why I thought it's pointless me handing you notebooks when the notebooks exist on the web and you can take it literally from the home page. So please let me know when you have all bookmarked this scikit-learn-optimize website. I will also put this website on the Slack for the time being. Let me put it on Slack. I'll of course add it to the website course portal. So if you
Slack would be nice. The live on is in the way of the.
Say that again, please. Kate, you
I'm
said
searching. I just wanted to check.
okay.
Okay, I've got it.
Yeah, and I've also posted it to on the Slack. So this is it. So guys, by now you must be feeling a lot of theory, but the application is so very easy, isn't it? Yeah. And the only thing I did, I'll post this notebook, is I gave you a contrast between using their library, their code, and not using it at all, just doing it the traditional way that people do machine learning. And they will hand instantiate this and try some random values or do some randomized search. So you can try all that, and then you can try this. Huh? I'll post this notebook in a moment. Now let's look at the next library that can do that. Okay, first of all, I'll just go through my other notebooks. If that is good, actually, there is one platform I like very much, which is the Axe platform. I feel that this is, of all things, quite mature, very mature, relatively speaking. Right? So they call themselves the Adaptive Experimentation Platform, Axe. This platform you can install by just doing pip install Axe platform. So I'm showing you how you can do a Bayesian optimization on any objective function. See, when we talk of loss for a neural network, etc., it is there. But as far as the Bayesian optimizers are concerned, they don't care. They just need an optimization function. So just to motivate and get you guys started, I took a very simple example that I hand created. Some of you may know about the sync function, sin x over x. I created a two-dimensional version of it. I just hand wrote a function, which is this. I have visualized it here. By the way, this notebook I'll paste. So rest assured that all of it will go to your website at the end of this class. So this is, what does it look like? Do you see that there is a unique minima there? All in blue? Yeah. So it is a highly nonlinear surface, but it does have a unique global minima, like absolute minima. Isn't it, guys?
Mm-hmm.
Maybe I'll make it bigger. Look at this picture, guys, even bigger. Can I make it even bigger? No. This thing has frozen. What a nuisance.
We can see it, Asif.
We can see it. Huh? Unfortunately, this browser keeps freezing on me, Chrome, with PyTorch. Let me try my luck with this. With Firefox, that seems to work.
Are you maxing out on your memory? Chrome takes a lot of memory.
No, you're looking at machines. This is a laptop with 64 gigs of RAM.
Okay.
So that's not likely to happen. Anyway, let me do it through this, because here we have a better luck. Okay, guys. So this is code. This is very simple code from Matplotlib visualization, 3D visualization. So in this, the important thing is that we have one big minima, and we have to search for this, right? So, and we will do it without doing gradient descent or any calculus whatsoever, just using Bayesian optimization. right? So you know that the solution is this. Let us see if Bayesian optimization can find it. So we say that there are two parameters, x1, x2. You know this. Remember this formula, x1, x2, right? Two parameters, x1, x2. I gave it a range -5 to 5, etc. And then I say that here is my function, the 1 minus Sankar. Remember this function, I just encoded this bit of equation. I just encode it into a function and I say, this is the definition of a function. Nothing magical here, guys. Is this looking easy? This is literally that equation writ large.
Yeah.
Right. P, of course, being the parameter map, right? It is the hash map of the parameters. And you're saying, look at this. And then this is the crucial method in the AX, which is why I like it very much. It has one optimized method. You give it the parameter space, the search. So parameters gives you what? The hyperparameter search space, right? The ranges of it. This is the box in which you have to search. X1 from -5 to +5 and X2 also -5 to. So it gives you the space to search. Evaluation function. This is the actual function, objective function. So this is the objective function will minimize. And are we minimizing or maximizing? So we are minimizing, minimizes too. In one fell swoop, it will do it and see how long it took. It took 6.67 6.67 seconds, which is really impressive for such a non-convex surface. Do you notice how non-convex it is? You can easily get trapped in one of these local minimas, isn't it? Nonetheless, with Bayesian reasoning, and so this brings up the fact that, see, remember I told you the trade-off between exploitation versus exploration? If you just did exploitation, let us say that in the beginning you randomly started here and a couple of points here, what would have happened? With pure exploitation, you would have stuck to this minima.
Local.
But because exploration is there, you also look at the other parts of the hypothesis space, I mean the hyperparameter space, you manage to get somewhere else, which took you gradually to the real minima, right? That is why the trade-off between, and how many trials it did? See, in just 20 trials, I mean, 20 points, 20 instances of searches in the hyperparameter space, it is already able to tell you that x1 is 0. See, we already know what the solution is. Solution is 0, 0, 0, right? X1, X2, and Z are all 0. Now let's see what it is coming out with. It is saying that X1 is this, X2 is this. Is it close to 0, guys? Almost, right? Would you consider this a reasonably good solution with just 20 trials?
Yep.
Yeah.
Pretty impressive, isn't it? And it is saying that the best value of the objective is this one, 000339, which is again 0. And it has pretty much guessed come to that. And see, guys, think about it. Completely without doing any gradient descent or calculus. Just through Bayesian reasoning, it has come there. Yeah? That is the magic of this, guys. Huh? Now, this other example I've taken from their website, they take a more complicated example and see where we know by doing calculus on this equation that the right answer of x1, x2 is 1 and 3. Right? Let's see what it comes out with. It comes out with x1 is equal to 0.964 and x2 is 2.9944. Pretty impressive for just 20 steps, isn't it?
Yes.
And Asif, what was the exit criteria for this right now? Why did it stop at 20? Because you said 20?
Oh, by default 20. Unless you set the number of steps to more, it will do 20.
Okay.
Yeah. So that is it. Those are all configurable parameters. But see, I've simplified it so that we can understand. And then you read up the documentation and you start throwing in more. Yeah? All of the other configurations you can change. How many of you, I mean, see, if you never have seen Bayesian reasoning, right, this is thrilling. All through the whole thing, machine learning so far, you have just been seeing the magic of gradient descent. And now you're seeing something else that also works very, very well. Isn't it? So obviously, those of you who took math with me remember all this Bayesian Markov chain, Monte Carlo, and so forth. Bayesian is just magic, guys. If you Google the word, what is the most important algorithm of the 20th century? Can anybody guess? Not people who have taken my course, math course. Any one of you, can you guess which is the most important, or most remarkable breakthrough algorithm, a most powerful algorithm of the 20th century? Can you guys guess? Anybody? Is it page rank? Is it this? Is it that? What would it be? Harini?
So the naive bias.
No. Anybody else?
Monte Carlo.
Who said Monte Carlo? Shiva. You're close actually. Give the full thing. Anybody else?
Is it to do with Markov and bias mix?
I can't hear the person who.
Markov and bias.
Markov and?
I'm just trying to mix Markov bias, something related to.
Yeah.
Markov chain Monte Carlo.
Markov chain Monte Carlo. It is the Metropolis algorithm. It is literally, and the reasoning is very close to this pure Bayesian reasoning. Just Google it up. The most important algorithm of the 20th. MCMC will come up, or Metropolis algorithm. It is Metropolis hosting algorithm will come up. It is a tragedy that we are taught all sorts of algorithms in college, but we are not taught what is arguably the most powerful algorithm. And that is the magic of Bayesian. People don't. Most people go through their entire career of computer science without ever doing it or realizing the power of it.
Sankar, can you mute yourself? Yeah, thank you.
All right. So now that I showed you the beauty of it in a simple statement, let me show a more complicated example with the Axe platform. This example is taken quite literally. So I'm posting all of these files, by the way, guys. This is their notebook. This is taken from their notebook. So what is it? Now we will look at the Axe platform applied to PyTorch, bring it to deep learning. How do we do that in the deep learning context? No different. You just do some imports. Now that you understand it, remember, what do we need? We need an objective function, guys, isn't it? Do you agree? We need an objective function and we need a parameter space to search. These are the only two things we need. Are we together? And so that's what we do. So in our language, what is this? This is our, like, given some parameters, you will return basically the loss for that, right? Evaluate some loss for that. So here they're taking a CNN. By the way, the CNN is a built-in CNN that they have in their tutorials. It's a simple CNN, and they are going to apply it to the MNIST dataset, right? So in your case, and this is your homework, guys, replace the CNN with one of the networks that you have already done in your prior labs. For example, you have a lot of autoencoders, you have a lot of these things, isn't it, guys? Right? Classifiers, this, that. So go replace this network with one of the networks you have done in your previous lab, you yourself has built. The rest of the code will remain the same. Just be careful about your learning rate, etc., etc. And then this is your hyperparameter range, right? That is it. You set up your objective function, your hyperparameter range, and you run it. And what does it say? It says something quite surprising. It says that for MNIST dataset, you need to set, and by the way, they're using a stochastic gradient descent with momentum. I just explained momentum to you guys. So learning rate is, of all things, a number you would never have guessed. I'd certainly not have come through grid search. Do you see? It is 0.000288, right? Is your best learning rate. This is your momentum. The best momentum is this, right? And if you use that, then your accuracy on the MNIST data set, it turns out that with a very simple CNN is already 93%, right? So
Asif, I see 20 significant digits for the 20 steps. Yeah.
Amazing, isn't it? Well, I wouldn't go that far. I don't think it needs to be that accurate. But
No, the learning rate is 20 significant digits. Beyond that,
this is it. Yeah, yeah. I wouldn't go that far. I mean, basically, you have to take it with the thing that okay, if I am here, 0.0028 is maybe this. Let's not go. Let's not get carried away. But okay.
I think for every step, I think it's dissecting by 1 digit. Actually, it knows the value for the 1 digit and for the next. For every step, I don't know,
Yes.
something like that.
Something like that. It's learning it. See, remember, it's doing the same thing. I taught you what it is doing. Yeah. There is the expectation improvement. There is an acquisition or selection function, right, that helps you choose the next point.
So this Tune CNN notebook is going to end up on the portal, and then our homework will be to replace the network with something we've done.
Yes, that's what it will be. And I mentioned it, by the way. I'll take you through in a moment. And so at this moment, just follow it, guys. Okay, just follow through with me. So now one nice thing I like about the Axe platform is, do you notice that it gives you a very beautiful rendering, a color map of the loss with respect to learning rate and momentum, right? So where is the highest score that you see? Somewhere here, right? Okay, you know that the best values are here. LR is equal to 10 to the minus 4, right? 10 to the minus 4. It is somewhere in this region. I wish it was, okay, there is a way to prevent this from happening. Compare data on hover, closes data on hover. Okay. Yeah, anyway, you can see that the closest, the reason with the highest score right here, it is just giving 16, 18, unfortunately. So what it has done is, these are the points at which it has sampled. It continuously seems to be going there. I wish I could avoid it. And the value of momentum was close to 0.28, isn't it? 28. So it's not letting me go there. But you're here. I'll just, terrible. Okay, I will not go there. And again, where is your lowest standard error? In this white region, which is again the same place, 10 to the minus 4, 2 into 10 to the minus 4, and 0.28 or so learning rate. So you can literally see that the island, the best hypothesis space is this. And do you notice something? Where are most of the trials done? Where are most of the dots? Is it in the best spot or in the worst spots?
Yeah, interesting. Best spots.
Best spots, right? So it has the nose of a greyhound, isn't it? Quickly it sniffs out that region in the hypothesis space which are optimal. And you can see that the hypothesis space is very, very complex. Do you see how many local minimas are there in the not the hypothesis space. I keep saying wrong things. Parameters, hyperparameter space. There are multiple minima sitting there, isn't it?
Yeah.
And yet it has managed to do most of the trials in the right place. So this is the beauty of the trade-off between exploration versus exploitation. So let us say that it started here. Yeah, look at this. The first trial was done here, right? The fourth trial, it seems to have been done here. Why is this saying 0, 0? 0th trial, first trial, fourth trial, right? After that, where is the fifth trial? It's here. So it did, this is your exploratory part, and then sixth is where, let's say, where did it do the sixth trial? Yeah, sixth trial is here. And so the moment it found this point, which seems to have a better, like a value, better score, let's see where it picked the 7th point. Look at this. It has picked the 7th point quite close by. Where is the 8th point? I wish I can find the 8th point.
So on the top?
The top. Yes.
Okay.
This is an example of exploration or exploitation, going from 7 to 8. Which is it doing at that moment? Is it doing exploration or is it doing exploitation?
Exploration.
Exploration.
Right. It is exploring. And when it explores, it realizes after a little while that this doesn't look as good. So the 9th point then goes to, let's see. And this is the thing, guys, you have to observe this plots very careful. Now look at this. 9th point is here, which is better than the 6th. And where was the 7th point? Forgot where 7th was. No, this is 8th. I wish we could number these points. It was explicit rather than hovering over it. Yeah, see, 7th is here, 9th is here, right? So you're in this island of stability here. It pretty much seems white. Now, after that, 10th, 11th is here, 10th is here, 11th is here. So now, what is advantageous, to do exploitation or exploration at this moment? You would lean more towards exploitation, isn't it? So 11th, let's see where the 12th is. I can't find the 12th one.
I think 12th is on the x-axis.
Oh yeah, 12th is here. So this seems to be shifting a little bit towards exploitation. It went far, and then 13th, 14th, right? But you guys get the main idea, right? 15th, 18th. Do you notice that the later 16th, 15th, 16th, 18th are all here? But it also does exploration. Even then, it keeps jumping out also. 14th is here instead, right? So, and ultimately, it's doing more exploitation after a little while than exploration. Let's see what is the 19th point. If we can, so 18th is, 18th is here, 15th. So 18th is pretty good. So anyway, I didn't know where the 19th point is gone. Oh, maybe here. Oh, here is 17th. Do you see how it is doing exploration far and wide? 13th is here. We were searching for it, right? It's hiding. Somewhere else we'll find the 19th point hiding. But in any case, once you have these points, do you see that your surrogate function is continuously making these contour plots? And looking at it, you don't pick one of these points as your best answer. This is what you would do in grid search or randomized search. Instead, what you do, you find the minima of the surrogate function, isn't it? Once you have drawn your surrogate function well, you find the minima. Your minima says that it is somewhere here, right? Right, somewhere here. Would you agree that the minima would be somewhere here? And you pick the minima of the surface, the actual surface. And that is the beauty of it, guys. And that's why I like this Axe platform. I like it because it helps. Do you realize, guys, that it is helping you see what is happening, how the Bayesian thing works once you learn to interpret it? How many of you find it fun?
Interesting.
It's very interesting, right? The only thing is you have to know the theory before any of these graphs make sense to you.
Asif?
Yes.
Have you read the book Honeybee Democracy?
Honeybee Democracy?
Yeah.
No, I have not. Send me a link to that. I'll purchase and read it. What is it about? Talk about it.
It's basically, like in the winter, they kind of split nest, and a group of the honeybees have to carry the queen to a new nest. And they basically get 500, like a distinct number of bees to kind of like do the exploration. And they send out maybe like 1/5 for one, expedition. And they will come back and show the other bees what they found.
Oh.
And then like at the next time, it will be like another batch. But there are cases where they fail and the whole nest just like die off.
Wow.
Yeah, like once they find like 2 perfect nests, and they will go different ways, and then like they will notice that they lost each other, and they'll come together again. And in the process, the queen is lost, and the entire colony is just gone.
Oh,
so are there like fail situations for patient?
It is possible. If your surface, if the true objective function, which is an unknown, if it is extremely bizarre, like very complicated, then it is possible that in spite of like if you don't do enough number of trials, you will and you will be stuck with a suboptimal solution.
No, but
the
I would
way
assume
this works is that, see, you're doing a trade. See, those of you who know simulated annealing and so forth, right? There is a pursuit of the optimal based on what you know, but there is also a probability of sort of evaporating out of that, jumping out of that to a random place, just to explore.
Yeah.
And because of a trade-off between these two things, these things actually work quite well.
So I was going to say the same thing as if I was going to say genetic algorithms. So it's a question of, I mean, to Dennis's question that he asked, there's no notion of a failure here, right? You will end up with something slightly less optimal.
Yes, that's all, yeah. But that also is still the good thing with Bayesian reasoning and the surrogate function is that is still helping you draw your surface, the response surface. You need all points, not just the points near the minima, to be able to faithfully draw a good surrogate function. So the only thing you do is do you notice how quickly it converges? Isn't it impressive? In just 4 trials, it has already reached a very high level of accuracy.
What is accuracy measured as?
A classification problem. How many mistakes, accuracy is how many correct answers you get in the classifying the digits.
So this is the accuracy of the final model, right?
No. The model, yeah, the model, yeah, final model. Yeah. For this, at the 4th trial, the accuracy is already 90% of the model.
No, let me restate. So the iterations are trying to pick the hyperparameters, and then you're building the model using that hyperparameter. And what you're seeing here is the accuracy of the model that you built.
No, it's the other way around. See, for each combination of hyperparameter, you train the model to its best value. Then you see its accuracy. So in the first trial, the accuracy was low. So you must have picked a really bad set of hyperparameters. Second time, it was a bit better. In the third experiment of hyperparameters, the model that was crafted had a better accuracy, and it is already reaching an asymptote. It is already at 90% by the 4th trial. The 4th hyperparameter combination that you pick, when you train your model using the 4th trial value, already you're achieving a very high accuracy once you train the model with these values.
I think that's okay. That's what I was saying. I don't know if I worded it differently. Yeah.
You happen to say the opposite way, actually. It's all right. I think you meant this, but yes, this is what it is. And then you notice that it's incremental. Very slowly, it's drifting to the optimal value. But can you imagine getting so close to the right answer, except by just fluke, if you were doing just grid search or randomized search or something like that? One major problem with those algorithms is you will never have the best solution, right? You'll be somewhere in the neighborhood of the best solution. Whereas this takes you much further. Like, these values that are coming out, they are not the kind of values you would pick normally in a grid search. Right? So that is the value of this. Now, you can apply.
If I had a quick question, in that you said you would train the model completely using that one set of hyperparameter, and then it would do the Bayesian search on different, set of that hyperparameter, but trains over the whole training data. For every point that was there on the graph, it has trained on the whole training data, right?
That is right. So remember, look at your objective function. That will reveal it. Let's think through this is our objective function. What do? Given one hyperparameter point in the hyperparameter space, parameterization, what do? You build a neural net, take the neural net, you train it with the data, with those hyperparameters set, the training data. This is your standard PyTorch code. You give it the training loader, data loader, you give the hyperparameters, you give the device CPU or GPU, then you evaluate. This is the one where you evaluate for, let's say, accuracy, right? This return evaluate, it will return the accuracy of the model.
So my question is, why do we need to go the whole training data, or so as to say, why do we need to go? Can't we batch by batch try out something much more effectively?
Good enough. No. See, the thing is that to train a model, once you have frozen the hyperparameters, you need to run it through a few epochs, no?
Okay, got it.
You need to, otherwise it will, it would be you prematurely stop. You don't know whether you are fully trained with that model, gotten to the optimal value for those hyperparameters or not.
Got it. Okay.
That's the point. So guys, this is it. And I'll post this code here. So here is your homework. Replace the CNN network used in this tutorial with some of the networks that you build. This is it, a very simple change. You realize that this is the homework that you will do will be just 1 or 2 line change. Import the svlib library, right? The svlearn library, and then the right import from svlearn library. There's that import this particular network that we have built. We have built quite a few neural nets. Stick it in there and see what hyperparameters it learns. And you will experiment with it, become familiar with it, guys. This is good. This space is very, very alpha at this moment. Things are rough and so forth. And I found that the Axe platform is pretty good in terms of maturity, reasonable maturity. And the one thing I liked about it is this. I love this plots.
It's a very nice
because
dynamic.
It shows me what is really happening with the data. So guys, we're getting to 10 o'clock and you guys wanted me to stop at 10. Let me show you some other things. So this is just one of them. Then there is auto sklearn, right? Auto sklearn, and again, actually, let me not even try with Chrome. God knows what happened. Let me go back and do auto sklearn. Very promising. People are talking about it and this and that and so on and so forth. My experience wasn't too good. When I tried to install this, it failed. But according to their website, it should have worked. It didn't. Right? But if you did that and you ran this code after that, it should have worked. If you look at this code is no different from that. The only thing is that you instantiate an auto sklearn classifier. So their approach is different. They are not saying do this Bayesian search cross-validation. They are doing it, but they're doing it under the covers. They are saying, pretend as though there is a new kind of classifier called auto sklearn classifier. Feed your data into that and you're done. Right? So you don't have to know anything about Bayesian optimization. They will take care of everything under the covers. That is their approach. Then there are other, let me show you, AutoKeras works. Right. So people who do TensorFlow and Keras is very easy. So here is it. I tried it on the California data set. I think they give you unstructured data. You can also do it on the image classification data. Actually, let's go and look at the image classification data. No different. See, you notice that all they do is AK image classifier fit predict. Let me increase the font. Guys, if you're used to scikit-learn, does this look easy? Image classifier, fit and evaluate. Nothing special, huh? Nothing special, right? So all of them tried for simplicity, but their maturity levels are at this moment very, very variable. So auto sklearn does work. Auto PyTorch though is, tried that. Where is it? It is really empty. Okay. I didn't put it. So this is the thing, guys, your homework. So now we should come to the homework since only a few minutes are left. Is there something that I missed? AutoKeras, auto sklearn, auto PyTorch. Okay, so there are more, guys. What I would suggest is, for example, I missed an important one, teapot. The other important one I missed is hyperopt. And those are all significant. Maybe I've opened those. So I will post some articles. This is a good article for you to review Bayesian and see if you can use this to understand it after the explanations you went through. So I will post a lot of information to the portal along with these notebooks. And this is auto sklearn, right? In theory, it should have worked, right? In practice, it didn't. So that's a separate thing. But then there is the HyperOpt. HyperOpt is very good. Actually, this will work. This notebook I didn't do because all I had to do is walk you through. So HyperOpt is actually very well regarded. It uses this method, the way that I mentioned, the TPE, the parse and estimators method. So now parse and estimator. So the code is very simple. So let's see if this code makes sense. Good old pandas and NumPy. So guys, the theory is you just need an objective function. Create an objective function that you like. And they have taken some polynomial here, right? This polynomial looks like this shape. So where is the minima? Somewhere between 4 and 5, 4 and 6, right? 5, maybe a little less than 5, 4.8 or something like that. It looks like the minima. Let's see if it is able to discover it. You give the domain, in other words, the parameter range. Here you're searching from -5 to 6, a range you will search for. Now, how different is the library? Let us go and see how hard it is to use. So you create a few trials, you decide, this is just keeping track of the history, trials and so forth. But the main thing is fmin. Look at this, right? You first come up with the function, minimize this function, come up with a surrogate function, and then try it out and find what it is. Just a couple of lines. It's a little bit more involved API. At the end of it, it comes out with, our guess was right, around 5, right? It comes out with this. So if you really think about these libraries, they all are doing, what are they doing? They are picking up the objective function, the domain, and after that is just applying it, right? And that you need the surrogate function and the acquisition function and implementation details. They're using TPE, and that is it. So this is for HyperOpt. Yeah? And when you notice it, when they do a lot of these trials, all those trials seem to gravitate towards the red line, which is the truth. Right? The mean is that. The values, the peaks at 4.8. So more of it when you read through it, but it's straightforward. And so this is for HyperOpt. Is there any other library that I wanted to show you guys? Yeah.
Asif, what about SIGOPT?
Yeah, see, there are many of these. Teapot is to be considered. SIGOPT. That one I haven't played with.
Okay.
So guys, why don't we do that? Could each team propose by tomorrow, each of your teams, project teams, propose a few libraries that you will investigate, post it to Slack. And so you realize that investing all of these libraries is not hard. All the APIs are simple. It is the maturity level. You'll have more struggle installing it than actually running it, right? Or understanding the code. Understanding the code will be straightforward. Remember, all of them just have an objective function, parameter space to search, and then some way to search it, some optimized method.
Oh, looks like Intel bought SIGOPT recently.
Oh, okay. Nice. So with that, I'll stop, guys. I'll post all of this. I should have posted some of this to the portal before, but I'll post it, guys, tonight or tomorrow morning. But do please form teams and do it. How many of you feel that this is a lovely thing and we must always use it?
Seems like a good idea.
It's a good idea, guys. It's one of those things that most people haven't woken up to, but I don't see a reason why they shouldn't and why everybody shouldn't be using it. Yeah. So we are in a different world. Forget about your grid searches and all that. And especially if you look at the SK optimize and so forth, they have made it so trivial for you. Just replace the word grid search with the word Bayesian search, bias search. That's it. And you're on the go.
So as if in the practical way that you use this, what I'm assuming is you need to somehow make the problem smaller, get a representative problem that you can put through the AutoML path to find the right hyperparameters. Because if your neural network takes, let's say, a few hours to train, and you're trying to do AutoML with that network, then you're looking at a few days, right?
No, actually, that is where it shines. Premjit,
How
see,
would you explain that?
let me just say, what happens today is these neural networks run for days. So there is no feasible way that you can do 1,000 experiments of grid search or randomized search. Because even if it takes 10 days, you don't have 10,000 days. That is the professional lifetimes of people, isn't it?
Okay.
30 years. So you can't do that. Now, did you notice how fast the Bayesian optimization converged? You saw that, right? Graph within 4 or 5 trials, it was already near the right answer.
Okay.
Right. So that is specifically the place where you would use automated machine learning even more. In fact, that is where it is designed for.
Okay. So I think the absolute measures that I was using in my head is a little big, right? I mean, so what you're saying is, yes, you have to go through the neural networks, whatever time it takes.
Yeah.
But if you hadn't used this Bayesian learning, it would have taken even more.
Right. It's a difference between 1 month. Like, let's say that you have to do 4 trials and each trial takes about 8 days, right? Versus taking 30 years, your entire professional career to find the best tuned model. Yeah. The differences are just mind-boggling differences. No? That
So
is
back
why
to the first statement that I said, then that is not the, so you still work with the full network. There's no concept of making it smaller. Yeah.
Yes, you still work with the full network. So guys, the point is that, we are entering now as this workshop finishes, I brought you to essentially the cutting edge of AI. We started with the foundations. You're realizing that, I hope by now, that we have covered all the topics and I'm leaving you at the cutting edge. The 2 topics remaining, time series, you guys had insisted from the last year's that we cover it, and it has some use in deep learning. We should learn it. So I won't be here for the next 8 to 10 days. So Dr. Chandra will take over and he'll do the time series. Then when I come back, quite likely I'll take off wherever he is. We have one last thing, interpretability of AI models. I'd like to finish that. And then we'll just focus 2 weeks of labs, projects. All of you finish your projects, guys, and present to each other. See, you have already started doing. You guys are learning from each other. And that is what I want to encourage in the last 2 weeks. I will be just moderating over and giving you guidance. But I want to just see in the last 2 weeks, you guys finish your project.
So, Asif, are you releasing the second project?
I will release the second project, yes.
Okay.
Yeah. So,
Asif, I have a question. So the Bayesian learning we used to optimize a particular model, but how does it relate to AutoML? Because we said
that is
AutoML.
automated ML. The auto part of it is finding. So there are 2 aspects of the auto ML journey. One is the hyperparameter optimization is at the core of automated machine learning. Automated means automatically tune the model to its most perfect hyperparameters. Right. And an extension of this idea is neural architecture search, which means that, for example, in the case of COVID, I showed you how many layers to have, where the residual connections would be. Those are also hyperparameters in some sense at the neural network level. And you can even design the neural network itself as a hyperparameter optimization problem. That's a neural architecture search in some sense. It's a very rough way of putting it.
I see.
You got that, no, Rafiq?
Yes, I got it.
That's the idea.
So, Asif, I have a. Okay, Balaji, if it's on topic, where I had a slightly different question, not on topic.
No. Exactly the nature paper that he talked about, Asif, and it's related to Premjit's question. There was a point in the paper where you said for a big data set, the neural search for the hyperparameter space will perform suboptimally compared to something else. So that's
Oh,
where
no, no,
my
no, no,
question.
no. You're mixing two entirely different things.
Uh-huh.
Okay, on yesterday, we covered this paper, which was on learned optimizers, right? There we are doing something similar. We are basically saying, forget about Adam and all this. Let's learn the structure of the perfect optimizer using a neural network in its own right. That thing, that part of the research is very immature at this moment.
Got it. Okay.
This is not. We are talking of a slightly related, a different topic, learned optimizers. Learned optimizers, we are at the beginning of a journey. Huh?
Got it. Okay, so I confused it. It's not all the high pass parameters, just the optimizer alone.
Optimizer itself, what should be the structure of the optimizer?
Got it. Okay, thanks.
That's a different thing. All right, guys. Anything else?
One question, not on this topic. So now I noticed that we're installing a whole bunch of libraries once in a while, right? Like right now for AutoML, there are a few things we're going to install.
Yes.
But I have not heard you mention the PENV, PyEnv, right? Do you have any?
Oh, the virtual ends. The virtual
the virtual environments.
Yeah.
Should we be looking at it? Would that make our lives simpler? Any thoughts?
See, the basic thing is I have avoided some of the, rigor that you enforce in the workplace. One of them is that whenever you start playing with some code or something, it is always a good idea to do it in a virtual end so that your host operating system is not sort of screwed up, right? So suppose you get one of these libraries and they're very immature. You don't know what it will do to your host system and the rest of your Python libraries. It's always better to do your experimentation in a new virtual env. Yeah. Generally, you should always use virtual env. And this is a general tradition, guys, to containerize or just to isolate. For example, nowadays we don't do bare bones deployment of anything. We use Dockerization. Yeah. Even if we test a software, we would go create a Docker image and take that around because it becomes portable and take it around. So in the same spirit, when you create a virtual env, when you do the setup installations within it and then do that, at the end of it, you can export all the required libraries of it in a requirements file. And somebody can reproduce your environment by just running the requirements file within their own virtual env.
So when we do the virtual environment, does it create a copy of existing what we have, or it'll create a fresh copy where only what we ask is going into it?
Yes, it will create a fresh copy where only what you ask goes into it.
Okay.
Besides the Python language itself, but everything else you'll have to start from scratch. So what you end up doing is you create something called a requirements file. And you run it. You do pip install -r requirements.txt, and whatever requirements are mentioned there, that environment will populate itself with those libraries.
And you don't see any issues with working in a Conda environment with that, right?
Yeah, Conda gives you the ability to create. I'll show you. Hang on, since you asked this question.
Yeah, you can create. I have almost 10 environments, so you can create a new environment or you can clone the environment.
Yes.
And the question came to my mind looking at when Asif said all these libraries we're going to look at are kind of immature. So I don't want any of them downgrading other libraries when I try to play with them.
Yes. I think you are already fatally lost because you are working on Mac. Okay, guys. So I'm kidding, by the way. Huh? Don't have Apple come and sue me. So you see that when you have your environments here, né? You can go on creating new environments. You just go at the bottom. Do you see my bottom left-hand corner? Do you see the create here?
Yeah.
Just create a new environment. That's it. And I won't click on this. It will ask you for an environment name. It will ask you what packages, etc. And then take a requirements.txt in which you have itemized all the Python libraries you want and run it. And they are done.
Okay.
So that's it. All right, guys. I'll just stop the recording now. See, guys, we have learned a lot of things in this workshop. Every time I do that, I say this is very important. And it is. To me, everything looks important. But AutoML is the future, guys. Huh? do take this topic very seriously. Do the labs. At this moment, actually, I'm too tired. I'll post it by morning because I have just a few minutes to have dinner and get into my India meeting. But and by the time I get out of that by 1:30 in the night, I don't think I'll have energy. So I'll post it tomorrow at some point.
Thank
And
you, Asif.
excuse me.
Thank you. That will be
Oh
fine.
yeah. Kate, I know, Kate, you are watching out for it. You'll be the first to know. So do the lab, guys, huh? And this is it. And now, of course, you're at the bleeding edge, so libraries will have immaturity and so forth. But to just as a basic thing, saying expertise with this thing, hyperopts, hyperparameter optimization, neural architecture search, all of these things of automated machine learning gives you a tremendous leg up. Just try putting it on your LinkedIn resume, LinkedIn profile, and just sit back and wait for the recruiters to call you. So, all right, guys, I'll just stop for now.
Thank you, Asif.